See, this is a course in relativistic quantum mechanics. In this course, what we shall do is we shall club two theories together. One is special relativity and the other one is quantum mechanics. So, special relativity, special theory of relativity is a successful theory in its own way, and quantum mechanics is also a successful theory in its own way, and they are very different. And this relativistic quantum mechanics bring these two theories together, and we will see that special relativity is and quantum mechanics are compatible with each other. Now, if we consider special relativity, special theory of relativity, this in its own way is successful, and it moves to GTR in its own way. And quantum mechanics, this also can be extended to nonlinear theories. Nonlinear theories in its own way. Now, if we want these two theories together, we will see that these two theories are not compatible. Quantum mechanics is not compatible with GTR as of now, and also special theory of relativity is not compatible with nonlinear or higher order theories of quantum mechanics. So, this is not compatible, as well as this is not compatible. Okay. So, the special relativity and quantum mechanics together, when we make it RQM, relativistic quantum mechanics, this stands at the borderline. These two are clubbed together and they are very much compatible with each other, and this stands at the borderline, the theory of relativistic quantum mechanics. And you will see, as we shall develop this theory, you will see that in quantum mechanics we can write Schrodinger's equation for a single particle, but once we develop this relativistic quantum mechanics, we cannot stop at a single particle, right? What we will be doing is we will be forced to move into many particle theory, and which is called the quantum field theory now, but that is not included in this course. And in quantum field theory, I tell you one thing. So when if the interaction is between electromagnetic field and charges, it is the quantum electrodynamics. So let's start. Let's begin with the notations we shall be using in case of relativistic quantum mechanics. And before that, the books which I shall refer is books. One is the Borken and Drell, volume 1. This is RQM, relativistic quantum mechanics. There is a volume 2, you can go through that and keep it as a set. Borken and Drell, volume 2. This is QFT. This is quantum field theory. You can use this book as well, quantum field theory. Most of the quantum field theory books, they have the relativistic quantum mechanics at the start. So quantum field theory, Peskin and Schroeder, S-C-H-R-O-E, Peskin and Schroeder. There are other books, a lot of books are there. You can go through J.J. Sakurai, Advanced Quantum Mechanics. That's the volume 2 after the Modern Quantum Mechanics. I will refer the books as we go along with this course. I shall refer the books. You can keep this as a test book. This Vorken and Drill. You can keep Peskin Schroeder. Okay. You can keep Weinberg. So let's write Sakurai first. J.J. Sakurai, Advanced Quantum Mechanics. Then you can. There is a book by Weinberg, Quantum Field Theory. Quantum Field Theory. You must check the name of this book. I think this Peskin Schroeder, the name of the book is Introduction to Quantum Field Theory. There is a book by Greiner, Field Quantization and Relativistic Quantum Mechanics. Two books are there by. There is a series by Greiner. There are two books. One is the Relativistic Quantum Mechanics and is the Field Quantization. Those two books are also good. A lot of mathematics are there. Now let's go into the notation part. Okay, let's go to the notation that I shall be using. Okay. The notation in case of special relativity, we know that we use the Minkowski metric, right? We use the Minkowski metric. So in case of STR, we use the Minkowski metric eta mu nu, and the I shall be using the Minkowski matrix like this, with the diagonal elements. It's a 4 cross 4 matrix, and the diagonal elements are 1, -1, -1, -1. That is the eta mu nu matrix will be 1, -1, -1, -1, and the rests are 0. Fine. Now say this metric is constant. This metric is constant. If you go to GR, see SR goes to GR in its own way, as I told you. Then in GR, what you have is, or the GTR, you have the G mu nu is a function of x mu. This x mu are this x mu, it's a function of x mu. Now, okay, this is not exactly, yes, this is a function of x mu, but actually this is a function of coordinates. These are G mu nu's are functions of coordinates and time. I'm not telling x mu as of now. I'll come to x mu. What are these things? You know these things. So G mu nu will be functions of coordinates. Here the matrix is constant, but here the matrix will not be constant. It will be in a curved space-time matrix. This is a function of coordinates. So, and this is also a rank 2 covariant tensor. You know what's a tensor, and you see this tensor is constant. So if this tensor is constant, that means the derivative of this tensor is 0. That means we do not need tensor calculus here in relativistic quantum mechanics. What we shall be needing is only tensor algebra. That means adding to tensor, contracting to tensors. You must know that tensors, any tensor can be written as a sum of symmetric and antisymmetric tensor. These things we shall be doing a little bit so that you get acquainted with tensors. But let's go to the notational structure first. So we are not doing any curl space time, so we are removing this GR part. So this is the matrix, this is a covariant tensor of rank 2. Now the 4 vector x mu, I shall be taking this mu, when I shall be taking this mu as, or this index as Greek, then x mu will run, x mu will be x0, x1, x2 and x3. Fine. Now when this index is Latin, that means ijk, so xi will be only space x1, x2 and x3. Keep this in mind. And x0 is ct, x1 is x, x2 is y and x3 is z. So this is coordinates. If you take a 4 vector, this is a 4 vector, x mu is a 4 coordinate, space-time coordinate. Suppose if you take a 4 vector, suppose the momentum for vector p mu, the p mu we know that it is p0, p1, p2 and p3. So what is p0? p0 is, we know that it is E over c, p1 is px, this is py and this is pz. You can write it like this as well, that is E over c p vector. This is the 4 momentum. Now this is the 4 momentum, this is the contravariant for momentum. Now you know from the tensor classes which you have done in the BSc that you can raise and lower these indices. So what will be the covariant momentum? What will be P0? Let's see this. So P0 will be P or P mu will be P nu eta mu nu. See, this eta mu nu is a rank 2 tensor, and if you contract this, if you contract this new index, you get a P mu. One thing, please keep this in mind. In this case, in this expression, nu is summed over from 0 to 3. Nu is a Greek index, so it will run from 0 to 3. This is Einstein's summation convention. Einstein's summation convention. That means you will write this as, Einstein summation convention means you don't need to write this sum. Don't need to write this sum. This is Einstein summation convention. That means the sum over repeated index is assumed. Okay. Now if you expand this, this will be P0 eta. See, I am here, mu is the free index. That means it appears on the left hand side. And this nu, I can change this color, please identify. This I am writing with yellow. This is the dummy index. This nu is the dummy index, but this mu is the free index which appears on the left hand side. No dummy index will appear on the left hand side. Please remember this. And whenever you do any tensor algebra or tensor equation you write, please take care of this fact that only a single dummy index, suppose nu here is a dummy index, only one pair will be there, right? Only one pair of dummy index will be there. If there is another dummy index, it will not be nu. You can't take nu as another dummy index, then you will not get the cross product. Cross terms you will not get. I'll tell you later how to handle this. Now, as of now, please expand this. So, this nu is 0 eta mu 0. Take any term. Right, please write this as free index. Take any term. Suppose we choose mu equals to 0. So this is P0, right? So this is P0 plus P. This is, see, let me write these dummy indices with yellow. And suppose this is P1 eta. If this is 1, this is 1, and this is 0 plus, we write P eta first. P eta first 1, then it will be 2, and 3, and this will be 0. The free indices are 0. Okay, and eta is a symmetric matrix. If you interchange these two indices, then it will not change sign. So now see, now this eta, let me write it explicitly here. This eta is diagonal 1, minus 1, minus 1, minus 1. That means only these terms are non-zero, rests are 0. So what is this term? This one is eta 0, 0. This one is eta 1, 1. This is eta 2, 2. This is eta 3, 3. Fine. Let's keep this. Let me take quantum mechanics. Keep this at the top. So these are only non-zero terms, rests are 0. So then this will be 0, this will be 0, this will be 0. Only this term survives. And what's the value of this? 1. So that is P0, right? So that's P0. That means this term, this covariant term is equal to this contravariant term, and this value is E over C. I am talking of this time component. Let's see one space component. Choose mu equals to 1. If mu equals to 1, then P what will be P1? P1 is P, here free index is 1, right? Let me again write like this, P-eta, I shall plug the indices later, shortly. Now if this is 1, then the free index will be 1, so it will be 1, 1, 1, 1. See, here mu is the free index. Now just plug in the value new, so that is 0, 0, 1, 1, 2, 2 and 3, 3. See here, this term is 0. This is a cross term. This is the value, this is non-zero, and what's the value of this? -1. So only this term is non-zero. This is 0, this is 0. So P1 will be minus of P1, that is minus Px. And similarly you will get P2 is minus Py and P3 equals to minus Pz. So the covariant components of this momentum are negative. So you can write it in a nutshell, in a smaller notation. This is contra. This is contra. Then what will be the co? That is E over C minus E vector. Space part is negative. Clear? So the space part is negative. You have lowered this index by this. This is one part, and remember this is a metric tensor which I am using to raise and lower these indices. This is a symmetric tensor. Symmetric tensor of rank 2. Symmetric tensor means eta mu nu is equals to eta nu mu. It is not necessary that all the tensors will be symmetric and antisymmetric. You can have tensors which is neither symmetric but not antisymmetric. But you can write any tensor as a sum of two symmetric and antisymmetric tensor. Okay. Just as you can write any matrix as a sum of a symmetric matrix and an antisymmetric matrix. Okay. Now another notation which I shall be using is the contraction between two vectors. You know these things, so I am going fast. Contraction between two tensors. So that is, if A is a tensor, or tensors, or a vector is a tensor of rank 1, or two vectors, you can two vectors, which is a tensor of rank 1. A scalar is a tensor of rank 0. So if these two, if you sum, right, this mu is a contravariant index and this mu is a covariant index, and this index is repeated, that means there is no free index here. So this is a contraction between two vectors, two 4 vectors. So that will be A0 B0 plus A1 B1 plus A2 B2 plus A3 B3. and I shall denote it as AB. There is no vector on the top. When I shall be doing a dot product of two vectors, so you know when two dot vectors are dotted, A dot B, this is a three vector dot, and this without dot I shall be using this notation. This is a contraction between two vectors, two four vectors, like this. It's a without this vector means small arrow notation, just A dot P. Okay, and this mu b mu, you can write it like this as well. So you can write b mu as, suppose a mu is fixed. Now what I can write in place of b mu? I can write eta mu nu b nu. Suppose I take the contravariant part of b and load it with eta. So what is this? This is basically b mu, right? So this is equal to, take eta mu nu on the left, a mu b nu. This is the contraction between two vectors mu and nu. There is another notation which is introduced by Feynman. You shall be coming across this, that is the gamma matrices. That is also a contraction. So let me tell you that as well. This is a contraction between two vectors, tensor of rank 1. Now contraction with gamma. Contraction with gamma matrices. Now see, this gamma matrices is a set of four matrix. This matrix will be used in RQM, and you will be denoting gamma mu as gamma matrices, set of gamma matrices as gamma mu, where mu is the Greek index and it will run from 0 to 3. Now if you contract any covariant vector, suppose p mu is a covariant vector with gamma mu, the typical notation is p slash. This is introduced by Feynman. Okay, and this gamma mu's are set of 4 cross 4 matrices. I tell you how gamma mu looks like. Gamma 0 will be I 0 0 minus I, where I is the 2 cross 2 identity matrix. Now if you write it with this in a block diagonal form, what shall you get? Just expand this, and this is a 2 cross 2 null matrix. Let's expand this. Sorry, let's expand this. This will be 1 0 0 1 0 0 0 0. This will be 0 0 0 0, and this will be minus 1 0 0 minus 1. So this is a 4 cross 4 matrix. The gamma i's are the rest of the gammas. So the gamma I is the Latin index. That means I will run from 1 to 3. So that will be also, actually let me write it in okay, this will be, sorry, the gamma i's will be 0 sigma I minus sigma I 0, where the sigma i's are the Pauli spin matrices. And if you again write it in a block diagonal form, actually here, let's write these gammas here. Gamma 1, that is, you can take a block. This null matrix will be a 2 cross 2 null matrix. This sigma I, gamma I will be sigma I. Sigma I means this, let's raise this index. Actually it is same, but still, okay. This sigma I is sigma x, and you remember sigma x is just a 0 1 1 0, and this is 0 minus 1 minus 1 0, this 0 0 0 0. This is gamma 1, and what will be gamma 2? Again take a block diagonal form. This side will be null, this side will be null, and this side is gamma 2. What is gamma 2? I think you remember the gamma 2 is the only imaginary matrix you have. Sorry, sigma 2. The sigma 2 is the only imaginary matrix you have. So this is 0 minus I 0, and this is 0 I minus I 0. Fine. And what is gamma 3? That is, again take it as a block diagonal structure. You have a 0 0 0 0 here, you have a 0 0 0 0 here, and this here you will have z, sigma z. Sigma z means 0 1 minus 1 0, and here you have the negative z, so minus 1 0 0 plus 1, right? So these are the gamma matrices, and you shall be contracting this p mu with gamma mu. That means this p slash is basically a 4 cross 4 matrix, right? Because this will be what? This will be p0, and p0 will be e over c. Let me expand this. So what will be p slash? P slash is p0 gamma 0 plus p1 gamma 1 plus p2 gamma 2 plus p3 gamma 3. Sorry, gamma 3. So that is p1 is what? p1 is e over c. E over c gamma 0. This is p0. p0 is e over c, and this will be minus px. I think you remember. That is gamma 1 minus py gamma 2 minus pz gamma 3. So these will be matrices. These matrices. This one, this one, this one, and this one. This is gamma 0. You will multiply this number with this matrix, and result is a sum of 4 cross 4 matrices. Sum of 4 cross 4 matrix, and this p slash will be a matrix. Fine. Now what I shall be doing is we shall be treating this del mu. Let me go through this notational part first. Now keep this p slash in mind. This you will come across this p slash I gamma mu matrices, which is contraction with p mu matrix, which got contracted with this p mu matrix, and you are getting p slash. You will be getting any 4 vector. If it is contracted with gamma mu, you will get that thing. Okay. Now there is another thing which I shall say. This will also come across del x mu. What is this? This will be denoted as del mu. See, this this label x mu is at the contravariant mu is at the contravariant position of this x, and this is basically at the denominator. So this is a covariant index, right? And del mu is basically eta mu nu del nu. Clear? Eta mu nu del nu. Then if we contract these two, what we shall get? That is eta mu nu del mu del nu. Okay? So that means if you plug this value 0 0, only the diagonal term survives, we know these things. So then it will be del 0 minus del 1 minus del 2 minus del 3. Now what is del 0 from here? See, del 0 is del x0, and what is x0? x0 is ct. So it's del of del ct, that is 1 by c del t. Clear? And what is del 1? Del x1, that is del x. Similarly, del 2 is del x2, that is del y, and del 3 is del x3, that is del z. Fine. So then what will be del mu? Then del mu is the, multiply these two, so it will be 1 by c square del 2 del t2 minus del 2 del x2 minus del 2 del y2 minus del 2 del z2. Now what is this? This is the negative of Laplacian operator. So this is 1 by c square del 2 del t2 minus del square, and this is also called the D'Alembertian operator or the box operator. Fine. So this is another thing we shall be using very much. So let's write it, that let's gist them together what I have done. Let's gist them together. This is the eta mu nu is the symmetric tensor of rank 2, symmetric tensor which I shall be using. The coordinates x mu are x0, x1, x2, x3, that is ct, x, y, z. Then del mu is del x mu, and del mu is eta mu nu del x mu, and del mu is 1 by c square del 2 del t2 minus the Laplacian operator, which is together called the D'Alembertian operator. This is the thing, and p slash is contraction with gamma mu matrices, and A mu, B mu, contraction of two vectors will be denoted as this. Also, P mu is E over C, P vector, and V mu is E over C minus V vector, right? So there will be other notations, and as we come across, whenever we will take H cross C equals to 1, I shall mention that, but as at the beginning of the course we shall keep everything intact, H cross and C, and once we and in the later course we will take H cross and C equals to 1, and we will recover those units using dimension analysis. This we have done in when we developed the theory of harmonic oscillators by algebraic method. So this I have already done. Keep this as a note. These are the main things we shall be using. Now we will go into the main part of this relativistic quantum mechanics. There are a few interesting stories how Schrodinger first wrote this Klein-Gordon equation. He got those energy levels, and but they didn't match with that experiment. We know today that those results are absolutely fine, they were legitimate. What Schrodinger did is he kept that equation aside and he took a non-relativistic limit of that energy level. I am talking of hydrogen atom, and he got the solution of this hydrogen atoms which perfectly match with the experiment, and so that was the story. After that, Klein-Gordon came up with this equation, and he wrote this equation which we know as the Klein-Gordon equation. I shall do it in the next class, and we will say that how they overcome the problem of negative energy. The negative energy was getting unbounded. As momentum increases, it is going to negative infinity. So how they arrest those negative energy by interpreting them as energies of antiparticles, in terms of antiparticles. These are very interesting stories. Then we'll go into the tensor form of Klein-Gordon's equation, continuity equation, and we will carry on with this course. Thank you very much.